We're going to take a look at something called the geometric mean in right triangles. And to get started, just talking about geometric mean here, it's a little bit different than the mean that you used to find in the past, the arithmetic mean, which was based on addition. And so a lot of times you would add up your terms and divide by however many terms you were adding. In this case, geometric is based on multiplication. And the way that we can find this is we could set up a proportion. So if you want to find the geometric mean between two values, a and b, we can say that a over x equals x over b, where x is that average that we're looking for, that geometric average. Now, there is a rewrite to this. If we end up cross-multiplying, you'll notice we'll take x times x, and I'm going to switch the order here, but we'd end up taking x times x during our cross-multiplication, and so we'd get x squared equals a times b. We'd get that when we cross-multiply. And so to solve for x, we would take the square root of both sides. So a rewrite of this formula could be that x equals the square root of a times b, which is essentially what would happen when we solve this proportion. So finding the geometric mean of two numbers like 4 and 6, pretty simple. It doesn't matter which one is which, but let one of them be a and the other be b. And so we can say that 4 over x equals x over 6. And so when you cross multiply 6 times 4, that's 24. And x times x is x squared. And so we need to take the square root of each of these, and we get the square root of 24 equals x. Now, we don't actually know the square root of 24, but we can simplify it. If you recall, 24 is 4 times 6, and 4 is 2 times 2, and 6 is 2 times 3. And so we could rewrite the square root of 24 as 2 times 2 times 2 times 3. And then if we look for a pair of factors, like we have right here, we could rewrite this square root as 2, because that's a pair of factors that we had, square root of 6. And the way I got the 6 was there was a 2 and a 3 that were not a pair of factors, and so I just multiplied them back together. So every time you have a pair of factors, you bring that factor out. Okay, so we can do that with just numbers like this. We could do it with a fraction. So we have an integer and a fraction here, and maybe we just skip the step and we jump straight to the square root. And we say x equals the square root of 9 times 7/3, which again is a rewrite of this formula up here. We could just jump straight to the square root. So if we simplify that multiplication, we have x equals the square root of 9 times 7/3 would give us a square root of 21. And you notice if you try to break 21 down to its prime factorization, you get 3 times 7, which is, as far as those break down, both of these numbers are prime. So in other words, 21 does not break down any further, and our final result is just going to be the square root of 21 here. So sometimes the square root will simplify, at other times it might not. So what I want to do next here is see how this idea of geometric mean can apply to a special setup in triangles. And so if you look at this diagram, you see we have a large right triangle. Triangle ABC is a right triangle with the right angle at C. And we've drawn in a segment called the altitude within this triangle. And there are 3 altitudes we can draw in. But when we draw it this way, we are splitting the original 90-degree into 2 parts. And what we've done is we've made a new 90-degree angle here, but also over here, right? If these are a linear pair, we have 2 90-degree angles. But what happens is we've now created 2 smaller right triangles inside of the larger right triangle. Okay, and when we have this set up, it's a pretty special setup. We have 3 right triangles, and these right triangles all have to be similar to each other. And you can think about that. As you look at the large triangle, it has angles A, B, and C, and one of those is 90 degrees. Well, this triangle on the right, let's get a quick look at it. This triangle on the right is also a right triangle. And so it has a 90-degree angle, just like the original large triangle did. But also, this triangle uses angle B. And because this triangle has a 90-degree angle and uses angle B, and the big triangle also has a 90-degree angle and uses angle B, these two triangles are similar by angle-angle similarity theorem. So the triangle on the right is a smaller version of the original large triangle. Now, pretty similarly, on the left, a very similar outcome is going to happen here. The triangle on the left has a 90-degree angle, just like the original right triangle did. And it uses angle A, just like the original right triangle did. And so because the small triangle has a 90-degree and uses angle A, and the big triangle has a 90-degree angle and uses angle A, this little triangle is similar to the large triangle. And so by angle-angle similarity, this little triangle is just a smaller version of the large triangle. So what we see now is this triangle on the left is similar to the big triangle. This triangle on the right is similar to the big triangle. And all three triangles end up being similar to each other. How does that help us out here? Well, if you remember, with similar triangles, the angles are all congruent, but the sides are proportional. And so what we're going to see are some sides are proportional to each other. And here's how I'm going to help us see that. So I want to label this picture. If you can do this with me here. I want to start with the big triangle here and give it some sides. So the big triangle ABC has a 90-degree angle. And because of that, the side across from the 90-degree angle is called the hypotenuse. And so I want to talk about the hypotenuse of the big triangle, which is down here. It'd be the side AB. So from A to B, that's our hypotenuse. And I'm going to abbreviate that as just HYP. Okay, so the hypotenuse is here, and we're talking about the original right triangle, the big one. Now, the other two sides of a right triangle, the two sides that are not the hypotenuse, are called the legs. And so we have a leg here and another leg here. And if we arrange our diagram like this to where the right angle is up top and the hypotenuse is on the bottom, we can see that one leg is to the left of the triangle and the other leg is to the right of our diagram. And so that is the reason I'm going to call this the left leg as well as the right leg. And I'm going to abbreviate that as well. So for left leg, let's call this LL. For right leg, let's call this RL. Okay, so those are the three sides of our big triangle. Now, after that, we have a few other pieces to label here. We drew in an altitude in the middle of the diagram. So I'm going to label our altitude. And let's call it ALT for short. Okay. And then underneath the diagram, our hypotenuse, you notice, has been split into two different segments by our altitude. We have the segment from AD, and I'm going to call that, similarly to before, I'm going to call this the left segment. And we'll put LS right there. And then over here, I'm going to put right segment for the other piece. And for that, we'll abbreviate it as RS. Now, essentially what we've done here is we've given every segment in the diagram a name. And so every triangle in this picture has a name for its side. So for this little triangle on the left, it has sides labeled as the left segment, the altitude, and the left leg. Even though this is technically the hypotenuse of the little triangle, we're going to reserve the name hypotenuse for this side down here. Okay, so something is going to happen now. We've said that these triangles are similar to each other, and that means that their sides are proportional. And so our similarity statements are given, that triangle ADC is similar to triangle ACB. And if you remember, what we've said about that is the first two letters here name a segment, and the first two letters here name a segment. And so this segment in our first triangle should be proportional to this segment in our second triangle. So this says that AD corresponds to AC. And our idea of proportionality is this comparison between the two triangles should be equal to another comparison in those two triangles. And so if we look again here, another comparison that I could set up would be AC, the segment AC in our first triangle, should correspond to the segment AB in our second triangle. And the reason I'm doing that, as you might notice, is that I'm pointing this out anyway, is that you might notice this proportion has reused the segment AC, this idea of cross multiplication of something times itself, which is exactly what the idea of geometric mean was, taking something times itself. And so that is how geometric mean is tying in here. With these similar triangles, there are some proportions that we set up to where we end up taking something times itself. And so let's see that happen again in our second case. If we look at the first triangle, we could say that in this case, DB is similar to CB, or is proportional to CB. And that comparison should be equal to the other. I'm going to look at CB in this first one. And as you notice, there's that cross multiplication of a value times itself, and CB relates to, is proportional to AB. So another proportion to where we cross multiply with a value times itself. Okay, and in one last case here, we have triangle ADC and triangle CDB, which happens to be the two smaller triangles in this picture on the left and on the right. And what happens here is if we look at segment AD and compare it to segment CD, that would give us the ratio of AD to CD being equal to another comparison. Notice how this one also uses CD. It's just listed as DC here over DB here. But another case of cross multiplication taking something times itself, hence the geometric mean. Well, if we replace these labels with the labels we have up in our diagram, we're going to see something. AD, we called the left segment. CD, we said, was the altitude. DC is also the altitude, and so maybe it's a little more clear now that we are taking something times itself. And DB is the right segment. Over here, DB, we just said is the right segment. CB is the right leg. CB, once again, is the right leg. And AB, we called the hypotenuse. And one last case here, AD is the left segment. AC is the left leg. Once again, AC is the left leg, and AB is the hypotenuse. Now you might notice here that these two comparisons are very similar to each other, these two proportions. And these two proportions are created when we compare the triangle on the left to the big triangle and the triangle on the right to the big triangle. And when we do that, when we compare one of the smaller triangles to the large triangle and the other small triangle to the large triangle, the proportions are almost the same. It's just, were you talking about the triangle on the left or the triangle on the right? And then in the last case, where we're comparing the two smaller triangles to each other, we are looking at that altitude that was used to create them. So these are three proportions that involve the geometric mean. We could talk about other proportions because in each one of these cases, we should be able to set up three comparisons because triangles have three pairs of sides. But these are the only ones that lead to this special outcome with the geometric mean. And that's what we're going to use in our examples. So when we talk about these diagrams with the geometric mean, what we're going to realize is that within these proportions, we had a few things that multiplied with themselves. So in this case, the left leg is multiplying with the left leg when we cross multiply. And so we're going to say the left leg is the geometric mean for the left segment and the hypotenuse. The right leg is multiplying with the right leg in this proportion. So the right leg is the geometric mean for the right segment and the hypotenuse, the other two values in that proportion. And then lastly, the altitude is multiplying with the altitude in this last case. And so we say the altitude is the geometric mean for the other two sides, the left segment and the right segment. And those are the three formulas we're going to use. So I'm just going to list them one more time back here. And so we have our three very specific formulas that can apply to the scenario where we have a right triangle and then we create two smaller right triangles inside of it by drawing an altitude through the right angle. We technically haven't learned anything new, though. I mean, we already know from similar shapes that sides are proportional, so we could go through these steps each time if we needed. We didn't need these formulas, but it is kind of nice to have them. And so to apply these formulas, it just depends. You have three options, and you to know which one you're supposed to use, it's just based off of what you've been given or what you know in a diagram and what it is you're looking for. And so we have a couple examples here we're going to look at using these three scenarios. Now, each time I will say it's nice to label your diagram and have it labeled like this to where when you have the two triangles, the two smaller triangles inside, we clearly have one on the left and we have one on the right. So it might be helpful to draw the pictures and then turn your paper so that it's set up like this one. And that's how I'm going to get started back here. I'm going to label my sides first, just like they were on the front. And so what we had said on the front was, and I'll show it to you one more time here. For the big triangle, it had a side of the hypotenuse, the left leg, and the right leg. So that's what we have here. For the big triangle, here's the hypotenuse. Okay. And then the left leg would be on the left side of this diagram, and the right leg would be on this side. Okay. And then let's see, we have an altitude drawn in the middle. So here's the altitude. And then down here, we have the segment on the left and the segment on the right. Okay, so there are several variables in this diagram. We have B, C, and D that we're going to solve for. And we also have some given information. So let's look at what we know. We know our left segment and we know the altitude. And so the question now becomes, do we have a proportion, a formula that involves the left segment and the altitude together? And if you look up, that was this last one here. The left seg over altitude equals altitude over right segment. And so that's the one I'm going to use. And maybe I get it set up first. So left segment over altitude equals altitude over right segment. When I substitute my values, I have a 5 for the left segment. Altitude is 10. Altitude, once again, is 10. And the right segment is variable C. Okay. And so one thing to note is after you substitute, how many variables do you have? Just one or more? And in this case, we just have the one, meaning we're able to solve this equation. So if we cross multiply, we'll take 5 times c, and that'll be equal to 10 times 10. Okay, divide by 5, and c equals 20. Okay, so now that I've found that, I'm going to go ahead and put 20 into my diagram just in case I need it. Okay. So what else can we find now? Well, we know the left segment and the right segment and the altitude. In this diagram, things we still need are the left leg and the right leg. Now, the left leg and the right leg each had their own formulas. You notice here, left leg was using this first proportion, and it involves the left segment, which we know. We were told that was 5, but it also says that we need to know the hypotenuse. And the same thing happens here. To find the right leg, we need the right segment, which we know it's 20. We just found it. And the hypotenuse, which we weren't given. But we do know the hypotenuse now would be the entire length from J to L, which is 5 plus 20. And so here we could say the hypotenuse is 25. So even though we weren't told the hypotenuse in the beginning, we do actually know its value now that we've found C. So we could use these proportions to find our last two variables, although I will also point out that if you choose to, you notice that these are right triangles, and so we could use Pythagorean theorem to find a missing side length if we wanted. But I'm going to go ahead and use our proportions here just to get an idea of how they work. So I'm going to start with finding that left leg. So the proportion that we could use is that the left segment over the left leg is equal to the left leg over the hypotenuse. And so substituting in, left segment is 5, left leg is D, equals left leg, which is D, over hypotenuse, which is 25. Okay. And then cross multiplying, 5 times 25 would be 125. D times D is D squared. And to solve for that, we need to take the square root. And we do not know the square root of 125, but it does simplify. If you go through the prime factorization, we get 5 square root of 5 equals D. And I've gone ahead and put that into our diagram now. So D over here is 5 root 5. It's a short way to say 5 square root of 5. We just say 5 root 5. Okay, last thing then would be to find the right leg, where we have the letter B. And so we have a formula for that as well. It's right segment over right leg equals right leg over hypotenuse. And the right segment we know is 20. For the right leg, we have the variable B. For the right leg here, also the variable B. And for the hypotenuse, we have 25. Okay, so this is another case of geometric mean taking something times itself. And you notice we only have the letter B in this equation, meaning we can solve for that value. So cross multiplying here, we're going to get 500 equals B squared. And when you take the square root, square root of 500 is not a perfect square, but it does simplify. Again, go through those steps with your prime factorization, and you get 10 root 5 for that square root. And there are the 3 missing values we were looking for. And again, one last time, we could have found B and D using the Pythagorean theorem, since these are right triangles, and that was a missing side in the right triangle. Okay, so for this last scenario, let's just set it up, but the steps are all the same. It's just like the one before. In this case, we have 4 variables going on, but you notice right away you were given the hypotenuse to be 15, and you're told one portion of that is 6. So that automatically should tell us that the other portion over here is 9. Right? Because 9 plus 6 would give us 15. So we actually don't have to do a lot of extra work all the time. We still want to keep hold of those old concepts that we've had. So now we know z is 9. Okay, to find those other values, we'll want to label our diagram. And again, this picture is not like it was on the front, to where the hypotenuse was on the bottom. Right, the hypotenuse is on the bottom. We have a little triangle on the left and a little triangle on the right. So you might want to redraw this and then turn your paper. But when you do that, here's what the labels will end up being. Here's your hypotenuse. And if you turn your paper, this triangle would end up being on the left. So here's your left leg and here's your right leg. And you can't see it right now because of how the picture is oriented. But if you turn it, you will. Okay, the segment going through the middle is always the altitude. And the other two segments are called the left segment and the right segment. And really what matters here is that the right leg and the right segment are both in the same triangle, and the left leg and the left segment are in the same triangle. Okay, so you have 3 formulas that you can use, and they're the same 3 as they were before, where we have our left segment over altitude equals altitude over right segment. We also have that the left segment over left leg equals left leg over hypotenuse. And lastly, that the right segment over the right leg equals right leg over hypotenuse. And so what we're going to do here is we're going to go ahead and just substitute in and see if any of these are solvable. So we know the left segment is 6, so we can put that here. For the altitude, we have y. For the altitude, it's still y. And then for the right segment, we knew what it was earlier. We knew it had to be 9 because 9 plus 6 gave us the hypotenuse length. So we can put a 9 for the altitude. So because this proportion only uses one variable, it's solvable. Okay, well, let's try that here. Left segment, we know is 6. For the left leg, we have x. So the left leg here is also x. And for the hypotenuse, we have 15. And again, this proportion only uses one variable, so we can solve for it. And then in that last case, the right segment is 9. The right leg is w. Right leg equals w, hypotenuse, 15. And again, one variable in this proportion, so this equation is solvable. So let's go ahead. I know I said I wouldn't, but let's go ahead and finish this. 6 times 9 is 54. And then y times y is y squared. And when you take the square root there, you get 3 square root of 6 equals y when you simplify it. All right. Next case, 6 times 15 is 90. X times x is x squared. When we evaluate the square root, that simplifies to 3 square root of 10. I know I'm skipping some of those steps, but that's just some algebra that we can take a little time to make our factor tree for. And then lastly, 9 times 15 is 135. And w times w is w squared. So we evaluate the square root here. And we end up getting 3 square root of 15 equals w. And again, earlier, I guess I should note that we were looking for z. Earlier, we had also found that z equals 9. And those would be our 4 values for our variables that we were given in the diagram. Okay, so just a little idea of geometric mean. This is actually probably the last time we're going to apply this idea in class, but it is an observation that we're making that ties in our similar shapes to this idea of a geometric mean instead of an arithmetic mean in our triangles.